Right. Okay, so what I'm going to do now, I'm going to go back and I want to just revise a few key concepts before we move forward. All right, so just give me, let's say, 10 minutes or so to just quickly revise, create a context for moving forward. So organic chemistry, and you do have these notes, I have posted these notes. Organic chemistry is the study of compounds of carbon, right? But excluding CO2, CO, carbonates, and cyanides. Cyanides are CN, all right? They are viewed as inorganic compounds. But for the most part, compounds that have got carbon in them and have a longish backbone are deemed to be organic, okay? There are millions of organic compounds because they're relatively easy to make because you can catenate carbons. You can keep on adding carbons, all right? And one of my favorite stories I like to tell is these very, very clever drug dealers or drug producers in the UK. They were very, very smart. What they did is they made designer drugs faster than what the authorities could actually create legislation. So in order to make a compound illegal, there needs to be a certain amount of analysis and testing and that. So, you know, whether it's the Drug Administration in America, I don't know what it is in the UK, but I watched a documentary on it where these, and I had this guy, he was dressed up in one of these masks. He was a PhD in chemistry, organic chemistry. He had a doctorate in organic chemistry. What they were doing is they were taking existing drugs, which are organic compounds, and adding one atom. It could be just another hydrogen, or it could be an oxygen, but it added it in such a way that it didn't actually change the functioning of the drug. But what it did do is it changed the name of the compound. And so it actually wasn't illegal because it was a different compound. And so they were creating these drugs. I would think the authorities have cottoned on to this, but that's the thing with carbon-based compounds. You can make carbon-based compounds pretty easy by things like polymerization and that. Okay, so there are millions and millions and millions of them, all right? As opposed to inorganic compounds, where there are between 200 and 300,000 compounds. So inorganic chemistry is the study of all the compounds that are not organic, okay? So it's all the compounds that are basically non-carbon based. Right, carbon, as we've discussed, is an amazing atom. It sp3 hybridizes in order to open up its valence structure. All right, here's a nice diagram of where the tetrahedral geometry comes from. These are the sp3 orbitals, the 4 sp3 orbitals, which is an orbital mix of the s orbital and the 3p orbitals in the valence shell. All right, if you look at bonding of carbon, we are not working with this now. We will work with binding or bonding energies in later on, but this is an indicator of how much energy is required to break bonds. And you can see the carbon-carbon bond takes 331 kilojoules per mole to break. Double bond, 590. Right? If you've got a carbon-oxygen bond, it's very, very strong. We're going to deal with what we call the carbonyl group. Very strong. You find it also with in carboxylic acids. And so carbon produces a very stable, when it bonds, it produces stable bonds. All right, we looked at the different types of formulae. We looked at molecular formulae. We have dealt with empirical formulae before. Condensed structural formula we have done. And then the structural formula, these two are very, very important. So we've done that already. What we haven't done is looked at the overall picture of all the organic compounds that we are going to deal with in this syllabus. And so this is a very important diagram, and it's a bit like a flow diagram. So the organic compounds that we're going to look at, we have looked at the hydrocarbons. Right now, the hydrocarbons only contain hydrogen and carbon. Okay, and we've looked at the three homologous series. We've looked at alkanes, which have only got carbon, single bond carbon bonds in their backbone. We've looked at alkenes, which have at least one double bond. And then we have alkynes, which have at least one triple bond in the carbon backbone. All right, we call those hydrocarbons. We've dealt with them. Now, if we substitute some of the hydrogens in an alkane, alkene, or alkyne, then we land up with a group of compounds called the haloalkanes, haloalkenes, or haloalkynes. They're also called alkyl halides, and we've dealt with that already. All right, generally speaking, we work with fluorine, bromine, iodine, or chlorine. Later on in our studies of organic chemistry, we're going to deal with the actual organic reactions that produce these. We're looking at things like addition reactions and substitution reactions, which you do not need to worry about at this stage. Our focus is going to shift to the carbohydrates, right? And the carbohydrates we're going to do actually quite quickly, because the foundation of our course has been laid with alkanes, alkenes, and alkynes. Remember, we've also done branching. So the carbohydrates, they contain carbon, hydrogen, and oxygen. What's the most common carbohydrate that we deal with on a day-to-day basis that we are aware of? Sugar, glucose. Yeah. What is the formula for glucose? C6H12O6. Carbon, hydrogen, and oxygen. Carbohydrate, hydrate, water, H2O, right? So you've got H's and O's, and carbo because there's carbon in it. Now, we are going to look at alcohols, which are basically alkanes, where one of the hydrogens, or two of the hydrogens, or three of the hydrogens have been substituted with what we call a hydroxyl functional group. I'm going to define that term now. We're going to look at organic acids, which vinegar is an organic acid, where we're going to work with the Cu group, to make sense just now. We might not get to the esters. We're going to do esters last because of the fact that we're close to exams, but I think we'll get to that. We're then going to look at the aldehydes and the ketones, which have got the carbonyl group, which is the C double bond O group in them. Okay, so you have this in your notes. This is a very nice visual summary of what we are doing. There are many more types of organic compounds than just this. If you study organic chemistry on university level, you will deal with books this thick with all different types of compounds, ethers and amides and amines and etc., etc., etc. Now, these two definitions are critically important. The first one that I want to look at is the bottom one. All right, but the bottom one refers to the top one. So firstly, the homologous series is a family of organic compounds which have the same functional group and whose consecutive members differ by CH2 in their molecular formula. All right, that is a very important definition. It's a definition that we ask often in tests and exams. All right, a homologous series is a family, apologies for that, is a family of organic compounds which have the same functional group and whose consecutive members differ by CH2 in their molecular formula. What that means is that every time you add a carbon into the backbone, there are two hydrogens that come with it. So if I go from, for instance, ethane to methprop to propane, I'm adding another carbon, but I'm also adding another two hydrogens that are bonded to that carbon. And that's why we say it differs by CH2. What do we mean by functional group? Well, a functional group, and this is also a very important definition, the functional group is, I just want to use a different color, the functional group of a compound is an atom or group of atoms that form the center of chemical activity in the molecule. So let me use an example of something that is pretty common, and that is alcohol, all right? So if you take ethanol, which is the alcohol that you find in wine and whiskey and brandy, etc., 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 that is got 2 carbons in it. We'll still draw it, hopefully today, C2, and it would normally have 6 hydrogens around it, if it were an alkane. But now, instead of one of the H's, we put in an OH. We substitute it. You'll see when we do reactions, a substitution reaction can actually substitute a hydrogen with an OH, right? By doing that, that OH becomes a reactive site. That COH gives that compound certain properties which people spend billions of dollars on every year consuming because of the fact that alcohol has an effect on them. Okay? That effect comes from the OH. And so that's what we mean by a functional group. A functional group is a group of atoms, it can even be one atom, which basically defines the chemical nature of that compound and the compounds in the homologous series. So the homologous series that's got the COH in it are called, drum roll, alkanols. Alkanes with hydroxyl. We call them alcohols. Alcohols are alkanols, okay? So they're alkanes with the OH. Right, methanol is a methane structure just with one of the hydrogens being replaced with OH. Right, so when we talk about a functional group, we are talking about a group of atoms that are basically defining the chemical properties of that particular compound. All right, are there any questions at this stage? These are not the only definitions for these 2 concepts, but these are good enough for the time being. Yes, Josh?
It says that CO2, or carbon dioxide is not an organic compound.
Okay, so it's a good question. So why would CO2 not be an organic compound? Well, I think it's historical, actually. I think it's just got to do with the fact that initially they weren't deemed to be in the organic group of chemical elements. They were basically grouped under inorganic. Right? One can debate about whether it should be organic or not. I think it's more a remnant of historical context. I think it's about history. You do get these remnants that come from the past. For instance, think of conventional current flow, the flow of positive charge in a metal conductor. We know today that that's not the case, that electrons flow, but the convention has remained because it was good enough, it worked. All right, are you okay with that? Cool, okay. So let's then move on. Right, hydrocarbons. You can split hydrocarbons into aliphatics and to aromatics. Now, we are not going to do that now, all right? Aromatics are where you have a circular, where your carbon backbone actually links up again and forms a cyclic compound. They tend to be very, very, very pungent. That's why they call them aromatics. Benzene. If you go and you look at drugs, things like steroids, hormones, drugs, the stuff that people are interested in, shouldn't be, but are, you'll find these benzene rings. They call them Kekule structures because Kekule was actually one of the people that actually figured this out. Then you get cycloaliphatics. We don't have time to do that now. Cycloalkanes, cycloalkenes, we're not going to do that now. It's not officially in the NSC syllabus, but at a later stage, we will do it from an enrichment point of view. We are dealing mainly with straight chain aliphatics, alkanes, alkenes, and alkynes. Right. Okay. In your notes, here are the prefixes: meth, eth, prop, but, pent, hex, hept, oct, non, dec. Right. And remember the general formula for alkanes is CnH2n plus 2. This is often asked in multiple choice questions. Right. We then looked at branched alkanes. This is on page 8. And my advice to you is, if you haven't mastered branched alkanes and alkenes yet, please go through this. The rules of how to do it are explicitly stated here. I think these notes will help you. I'm going to go through the homework and I'm going to be applying this, so I'm not going to spend too much time on that. Right, there are nice examples here. I'm referring to the notes because we haven't done so thus far. All right, what we've been doing is in the notes. All right, so I want to move on to, we've done alkenes. With alkenes, here's a definition of alkenes. Right, alkenes are unsaturated hydrocarbons that contain at least one double bond between carbon atoms, and their general formula is CnH2n. That is also often asked in multiple choice questions. By the way, what is the difference between saturated and unsaturated compounds?
When let's say when you're drawing your structural formula, and then when it lines, let's say one hydrogen on top and the other one is empty, then it's unsaturated.
Yeah, that is true. And the reason why is it that it's that case? Why is it that the carbon doesn't have two hydrogens attached to it, but only one? Because of double and triple bonds. Spot on. So as soon as a hydrocarbon has got double or triple bonds, it becomes unsaturated. It means that it's not saturated with hydrogens. The maximum hydrogens is not there because of the double or triple bond. Josh?
So if they put different atoms instead of hydrogen, is it still considered unsaturated or saturated?
That is a very, very, very good question. I would say if it hasn't got double bonds, it is saturated.
Even though it's not full.
If it's got double bonds, okay, if it's got double and triple bonds, it's definitely unsaturated. Okay, we can debate about, but I think it's still saturated, even though it's got one of the hydrogens has been replaced with a bromine. But I may be wrong. I don't lay claim to being the world's greatest chemist. If you find out for me and confirm it, I would appreciate it. Okay.
Like now.
Now's not a bad time. All right, let's move on. Then toward the end of the last lesson, I referred to alkynes, and alkynes tend to be very reactive because of their triple bonds. All right, and alkynes are compounds that contain at least one triple bond, and if you have a single triple bond, then the general formula will be CnH2n-2. The first compound in the homologous series of alkynes is ethyne, also known as acetylene. I mentioned with the oxyacetylene torches. Okay, it is a gas, very, very reactive. All right. Any questions? Can I look at the homework? All right. So let's take a look at practice 5. Complete the following table. All right. So we have C3H4 is the molecular formula. The condensed structural formula is CHCCH3. My advice is to expand that into the structural formula. Okay, so let's do that. So we've got 3 carbons. 1, just get my 1, 2, 3. If we work from left to right, this is CH. So I'm going to include the H. All right, so we've got the CH, that's done. We have C. All right, so between that C and that C, can you see there's no hydrogen? So there's a triple bond there. Let's do the circle test. Around that carbon, 1, 2, 3, 4 bonds. around this carbon, 1, 2, 3, 4 bonds. And then the last carbon has got H3. 1, 2, 3. Let's count. 1, 2, 3, 4. So the structure is correct. Okay. Now let's name this compound. Meth, eth. I am going to say that this is prop ine. I have purposefully not put 1 in there. Why? That's the only compound you can get. Because if I put the triple bond there, then I count from right to left. It's still prop 1 ion. It's not wrong, but it's not necessary. There is only one propine.
So if you were to write pro 1 on the test, would you get the marks for it?
He's just asked that. You would get the marks for it.
I would get the marks.
Well, I don't think I should differentiate between you or anyone else and not give you the mark and give them the mark. That would be wrong. You get the mark. It's not wrong. So to write one propine is not wrong. To write prop 1 ine is also not wrong, but it's not necessary because there's no prop 2 ine. Okay, let's move on. The next one is 1 butene, but, meth, eth, prop, but. So we're going to have 4 carbons. 1, 2, 3, 4. The triple bond is going to be between carbon 1 and 2. Right? We now use the circle test. 1, 2, 3, 4. There will be a hydrogen. 1, 2, 3, 4. It's fine. 1, 2. So we're going to need 2 hydrogens there. 1, 2, 3, 4. We're going to need 3 hydrogens there. Right. So what we have is we're going to have CH. We're going to have C. Right. So we've got CH. We're going to have CC. We're going to have CH2. All right, have I got this right here? 1, 2, sorry, I put 1 carbon in too many. All right, should be 1, 2, right? That carbon there should have a CH2. My bad. CH2 and then CH3. Let's just look. C, 1, 2, 3, 4. Guys, it's rude if I'm talking and you're talking and vice versa. Okay? So it's CH and then it's C, CH2, CH3. And the important thing is with condensed structural formulae, the assumption is that all the carbons are bonded together.
I'm just a bit confused with condensed structural formula. When do we start using brackets?
You use brackets, it's a good question, when there's repetition or indentation. Okay, repetition would be if we had, let's say, another CH2 in here, then we would say CH2 bracket 2. Or if we had CH2 5 times, it would be bracket CH2 bracket 5. But we don't include the last one, because the last one is a CH3. Okay, so we wouldn't say CH2, 2, and then an H.
And then when it's in the inside, because like sometimes I use a bracket and it goes CH and then 2 inside that bracket.
Okay, when we get to branching, and you want to do condensed structural formula with branching, then you start to use brackets to indent a branch in the condensed structural formula. All right, Josh.
For the brackets, must you put the 5 as a coefficient or as a subscript?
It's a subscript. It's a subscript. Good question. Okay, pent 2 ion. We're going to do this one quickly. Oh, molecular formula. 1, 2, 3, 4. Okay, so the carbons are C4, and it's going to be H6. 1, 2, 3, 4, 5, 6. And remember, the general formula for for alkynes is CnH2n minus 2 if it's only a single triple bond. Okay, let's do pentyne. Pentyne is going to be 1, 2, 3, 4, 5. Right? Pent 2, counting from left to right, 1, 2, 3, 4, 5. So between carbon 2 and 3, we put a triple bond. Right, and now we go 1, 2, 3, 4. We use the circle test. Right, hydrogens. 1, 2, 3, 4. No need for hydrogens. 1, 2, 3, 4. No need for hydrogens. 1, 2, 3, 4. We need 2 hydrogens there. 1, 2, 3, 4. We need 3 hydrogens there. It's always a good thing to go back. Just check. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay. Now let's do the condensed structural formulae. So we're going to have CH3, CC, okay, CH2, all right, and CH3. Now, some of you might say, but Mr. D, why don't you just make this C3? Yeah. I don't think it's wrong, but I don't think we want you to do it in NSC. We want the carbons to be explicit. But I think it would be wrong to mark you down, but I think it's because they are bonded to each other. At least the C2 I would accept. The C3, because you need to have the H2 bonded to that C. I don't think C3 would be right. I think C2 could still go down as being correct.
Yeah, I did do C2.
Okay. All right. If I was marking, I would fight for that wasn't wrong. Whether that would mean anything, I don't know, because I don't mark chemistry, I mark physics NSC, but I would say that isn't wrong. Okay. Right, molecular formula, we've got C5, and it's going to be H, 2 times 5 is 10, minus 2 is going to be 8. Let's see. It's going to be 1, 2, 3, 4, 5, 6, 7, 8. Oh, I have a question. What is the difference between propyne, butene, and pentyne when it comes to the amount of carbons and hydrogens? Between there and there, how many carbons and hydrogens did we add, Taylor? We added a CH2, huh? Can you see we added a CH2 and then we added another CH2? Where did we add the CH2? Let's just see here. This was 1, 2, 3, 4. This is 1, 2, 3, 4, 5. All right. Can you see here there was a CH2 between the ends? And have we added another CH2? I just want to see 1, 2, 3, 4, 5. This is 1, 2, 3, 4. All right. But can you see we've got an extra hydrogen, an extra 2 hydrogens? We've added another H2. Can you see there? Here was CH. Now we've added a CH2. And that's why when we define the homologous series, we say there's a family, a group with the same functional group that differ by CH2. Are we okay with that? All right. Okay. Now, ladies and gentlemen, alkyl halides we have already done. This is when we substitute one of the H's with a halogen. All right. So if you want to look at that formula there, all right, the X will be either fluorine, chlorine, bromine, or iodine. That's if you have one halogen atom that's substituted.
Sir,
Yes.
is that our curriculum stops at I or AT?
No, we don't do AT. I think practically AT. I think AT is a very, astatine is a very, very scarce and rare element.
For naming of these complex molecules,
Didn't you mention that we had to have numbering in there?
Yes, you do. We do. You do. All right. Just out of interest's sake, nowadays it's not such a big thing because mankind has actually moved away from CFCs. But CFCs were like when I was at university, CFCs were a big thing because they were damaging the ozone layer. All right. But CFCs are chlorofluorocarbons, and they were used in aerosols and in refrigeration, and they were basically damaging the ozone layer because they react with ozone. All right, practice 7. I'm going to go through these quickly. Right, so we would like to tell me what the name compound is. It's cool to be wrong in science because it means, Dido, that you're trying.
That's one bromoethane.
One bromoethane. It's ethane or ethane, doesn't matter. Tomato or tomato. Okay, so it is 1 bromo ethane or ethane. Whether you say ethane or ethane doesn't matter. Ethanol doesn't matter. 1, 2 is F. This way. What is the backbone? Meth F. Is there a double or triple bond? So your carbon backbone is an ethane structure. Your bromo is on carbon 1. Yes, Amikate.
So do you have to have one?
In this case, you don't. Because in actual fact, no matter where you put the bromine, it's going to be the same compound.
But can you say something like bromo 1?
No.
Okay.
You don't put a 1 between the bromo and the ethane. No.
Yes.
It goes in the front. Okay? That's the nomenclature. All right, well done. If we look at this one, what is the carbon backbone? Ethane. So it is going to be ethane. Okay, now you could have a difference because you could have both bromines on carbon 1, then would be 1,1 dibromo. But now you've got them on 2 different carbons. So yeah, if we're going to say this is 1,2 di, let me just give myself more space. 1,2 dibromoethane. You could have an isomer where this bromine was on that carbon, it would be 1,1 dibromoethane. Are we okay with this? Right, next, let's go to this one. Now, if we look here and you look at this, a lot of you are going to want to turn around and you're going to want to run away. All right? Because it looks horrible. All right? It's a bit like if you climb onto a rugby field and you climb onto a rugby field and you're about to play, and the next minute the team comes on and you see these giants. And you go like, how am I ever going to tackle that? All right? How many of you have played rugby? Have you ever been given 50-0? It's not a pleasant experience. I have experienced it. Sort of as an indicator that I should give up rugby and not play rugby, which I did. Okay. All right. So the first thing you need to do, and this is in the notes, you need to find the longest carbon chain that has the substituents in it. Okay, so let's look at the substituents. We have got a chlorine there. We have an iodine there. We have a bromine there. All right. Those are the substituents. So the longest chain that's got them all in it is this chain. Josh.
What would happen if there weren't any substituents?
Well, then you would still choose the longest chain. It's a very good question. You still choose the longest chain.
The chain branches into like 2 equal parts, then.
That's a very good question. You choose one of the parts and then the other part becomes a branch. We are going to need to position them. The question is, what numbering system are we going to use? So this is my advice. All right? I suggest before you put everything together in the name, you do the following. You say, okay, we've got a chloro, so I'm going to write chloro there. Right? We have an iodo. All right, I'm going to write iodo there. We have a bromo. Right, I'm going to write bromo there. Right? But there's something else that's here that's unusual. What is it? It's the ethyl or ethyl group. This is an alkyl group. So can you see that here we have ethyl or ethyl, right? And those are the unusuals that are standing or are in the position of the normal hydrogens that would be in heptane. But now we've got to decide on numbering. With alkyl groups and with halogens that are substituents, they have equal priority. So I'm going to start by numbering on this side. 1, 2, 3, 4, 5, 6, and 7. All right? Now, if we number in this way, the chloro is going to be 1 chloro. The iodo is going to be 2 iodo. The bromo is going to be 5. And the ethyl is going to be 4. Do you agree with that? Yes, no?
Sir, do we not do it alphabetically?
We'll get to the alphabetic. We do work alphabetically, but let's first work with the positioning. Right. If I number the other way, 1, 2, 3, 4, 5, 6, 7. Then the numbering is going to be as follows. And what I'm going to do, I'm just going to do it on the right-hand side here. The chloro becomes 7 chloro. The iodo is then on carbon 6. The bromo is on carbon 3. And the methyl will be also on carbon 4. Okay. Now, in IUPAC naming, we go for the lowest set of numbers. Which one of these numbering systems produces the lowest numbers? Left to right. You see, from right to left, we land up with 6 and 7. But from right to left. But from left to right, we've got 1, 2, 4, and 5. It can become tricky when you've got lots of numbers. But here it's quite clear, this is lower than that. So we're going to number from left to right. Now, as Noah correctly said, we're now going to construct our compound's name in alphabetical order. So we are going to look at the first letters in our substituents. So bromo comes first. So this is going to be 5-bromo. So the bromo is done. Then is the C in chloro. So that's going to be 1 chloro. Then it's going to be the ethyl. So it's going to be 4 ethyl. Then it's going to be the iodo. It's going to be 2 iodo. Notice that I put hyphens on either side of the numbers. Right. Then comes the heptane. So I say that reading organic chemistry is a bit like reading Arabic or Mandarin. You read in reverse. You do read Mandarin in reverse, eh? Not anymore, is it? Okay. Is it you read from left to right? Okay, so Arabic, I think Arabic you read from right to left, okay? So your backbone sits at the end. Now, some people will say to you, it's not important whether you have a space there or not, all right? My advice to you is to don't include the space, okay? As to whether they're going to penalize you in NSC exam, I doubt it, okay? Dr. Rousseau, you can always ask Dr. Rousseau, but I doubt it if you leave a space. I don't think they are that particular, but to be safe, rather leave the space out. Okay, questions? Josh?
Will they penalize you if you have a hyphen?
Yes. Yeah, rather leave a space, don't put a hyphen. Dido?
So just going back, you know how we, for the 1.2 dipole, so then we're only working with di and tri, we won't go more than di and tri.
Absolutely, we will not go more than try. You can get tetra, but we're not going to go more than that. Okay.
So C4, does it mean 3 lines? Is that
What do you mean 3 lines?
like the circle test?
Okay, let's just see here. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3. Spot on. There's a hydrogen missing there. Well done. Can you see that in actual fact there should be a hydrogen? It doesn't change the name, but you're absolutely right. Okay, let's see. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay, thank you. Well done, Kavar.
So like all this like heptane and protein stuff, we're going to be giving it that.
Will you?
Be giving it.
No, not at all. You need to know it. You need to know the prefixes. It does not get given to you in an exam. Meth, eth, prop, but, pent, hex, hep, oct. NSC goes up to oct.
Yeah, I saw in the notes that it was a way to distinguish the difference between
Guys, please just listen.
between the separate group that goes style and the main group, which is the heptane. So what do we use in sound field to distinguish the difference?
You find the longest chain that's got the substituents in it. The longest chain. Yeah. Okay, guys, we do need to move on. Right, let's move here quickly because I want to start with alcohols today. All right, so any other questions you can ask me after the lesson. So if we look at this one here, here is a very, very clear and important rule. And Trent, this follows on from what you've asked. When there's a double bond in the structure or a triple bond, your longest chain has to include the double bond. Even if it doesn't land up being the longest chain in the structure, the backbone, according to our naming system, is the one that's got the double bonds in it. So here, it's not really a problem, but there is a mistake here. Did anyone pick up that there's one too many hydrogens here? All right. Now, I've used these notes for years, and I've never taken them out, all right, because I actually purposely haven't taken this one out, because it's important to check, even when a structure is given to you, to use the circle test, like Kavar did just now. Yes, no?
So you go put the on the other side. The other one's missing one.
I'm not with what you're asking.
No.
Okay. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4, 5. That is wrong. So one of these hydrogens shouldn't be there. All right? 1, 2, 3, 4. Now, we are going to choose the longest chain. Okay, there is actually only one. Now we're going to number. Do I number from left to right or right to left? Why? Mbali, why do I number from right to left?
Because that's the smallest numbers.
It's going to give us the smallest number. That's the descriptor of where the double bond is. So numbering like this, 1, 1, 2, 3, 4, 5. This is going to give us meth, eth, prop, but, pent. So this is going to be pent 2 in. All right, let's take a look here. Can you see meth, eth, prop, but, pent? And the in, the double bond is between carbon 2 and 3. Right, now we have got two halogen atoms that are in this structure. We've got bromine and we've got fluorine. Right. The numbering, we have dedicated our numbering system based on where the double bond is. We can't change it now. So if we had numbered this way, 1, 2, 3, 4, 5, then this would have been a 3, and that would be not the lowest number descriptor. Okay. So now, look at the bromo. This is going to be 1 bromo, 1 bromo, and it's going to be 4 fluoro. So now we work, and we're going to work alphabetically. Bromo before fluoro. Okay, so what I'm going to do, I'm going to make space here. I'm going to say, okay, so this is going to be 1 bromo, and this is going to be 4 fluoro. Pent2ene. Who got that, just out of interest sake? Well done. Wasn't too difficult. I think this one was way more difficult. This one was way more difficult. Even though it was basically there was no double bond, it was more difficult. Yes, Josh?
Is it fine if you had after the bromine you did -2 -pentene?
That would be fine. So what Josh is saying is you pull the 2 out here, and then you have -2 -pentene. That would be fine.
So it's fine when you have a number.
It's fine. If you pull this out and put it in the front there, it's fine. That is acceptable. Yeah. But what's not acceptable is if you just put, instead of between the fluoro and the pent, you put a hyphen. But if you put a -2 pentene, then it's fine. Okay, this is a language. Okay. We're almost done. Let's look at this one here. All right. Now, we go here, we go, okay, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. The diagram is okay. All right. Now, the longest chain is obviously that one. It's got 2 double bonds, right? It's meth, F, prop, but, pent. Okay, so this is going to be pentadiene. If you got the di, you need the I find that personally, I find that with all due respect to IUPAC, I find it a silly rule, but it's a rule nonetheless, which I can't change. Okay, now let's look at the numbering. If I number left to right, 1, 2, 3, 4, 5, okay, then this will be 1, 3. If I number the other way, 1, 2, 3, 4, 5, it will be, it's going to be 2, 4. So can you see, you're going to get a lower numbering if you go from left to right. So this is going to be penta 1, 3 diene. Are we okay with that? Does it make sense? Okay, cool. And then we've got our substituents. We've got chlorine there, and we've got chlorine there. So we've got dichloro, and we've got a bromo there. Let's make it bromo there. Do we have anything else? Hydrogen, 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 chlorine, hydrogen, hydrogen. Okay, so, yes.
Sorry, sir, I missed it, but why again are we going left to right, not right to left?
Okay, can you see we're describing the double bond between 1 and 2 and between 3 and 4? If we went from right to left, it would be 2 and 4.
But with the halogen...
the halogens don't come into play. It's a good question. I'm glad you're asking that question. When it comes to the numbering, you go based on the lowest numbering for the double bonds.
And then if there's no double bonds, then you can do
if there were no double bonds, then you would go based on what's the lowest set. There's a priority listing here. Double and triple bonds are take precedence. Yeah, good question. Good question. So you commit to your numbering based on the descriptors for the double bond. You want the lowest number descriptors for the double bonds. Thank you, Declan, for asking that. All right, so now what have we got here? We've got a 5 bromo we have a 5-bromo, and we have a 5-bromo, and we've got 2,4 chloro. Is that correct?
When do you use the other? Am I confused?
We're not going from right to left. And the reason why we're not going from right to left, if we go from right to left, then this would be 2,4. If we went from right to left, then this would be 2,4 diene. And can you see that's a bigger number set than that? Well, it's bigger numbers. It's a set with bigger numbers than that. Are you okay with why we're going from left to right? Okay, now, so using alphabetical order, we don't take the D of the die into consideration. These little tricks. So what are we going to get here? We are going to get, this is going to be 5-bromo, and it's going to be 2,4 dichloro, and you can see it's a little bit of a push there. All right. Okay, so if we rewrite it, it's 5-bromo, 2,4 dichloro, and it's going to be, and you could also say 1,3 pentadiene, but we prefer you to do this penta 1,3 diene. Okay.
So,
yes.
when you read the names, do you say the numbers or just?
You do say the numbers. You do say the numbers. The numbers are important. Okay, now, ladies and gents, I want to push on. We've got about 20 minutes left, and I want to do alcohols with you. All right, yes?
Do we do ethers?
No.
Okay.
Ethers used to be in the syllabus, but, you know, it's been taken out, and the reason is that it puts people to sleep.
So we do.
You didn't you didn't catch my joke. Ethers were used as for narcosis, to put people asleep. Okay. An ether is where you've got COC, where the O sits between two alkyl groups. You got my joke. Thank you. Thank you. Okay. All right. Let's move on. Let's move on to the functional groups. Yeah, is a different definition of a functional group. It's a group of atoms that are common to all molecules within a specific homologous series and is responsible for the chemical properties of the compound. It's saying the same thing. This particular table is really very, very important. Okay. I want us to look at this table, and I want to adjust the table, please. Right. When we say this is the functional group name, I want you to change that. This is the homologous series. And a common mistake is that learners mix up the difference between a functional group's name and the homologous series. Okay, so let's look at this table. The homologous series is called the alcohols. The structural unit is OH, but the functional group name is the hydroxyl group. Okay, so the OH is the hydroxyl group. Okay, the carboxylic acids are the homologous series. The structural unit is what we call the COOH, C-O-O-H, but this is known as the carboxyl group. The esters, which we will eventually get to, the functional group name is known as the ester link. The ethers we no longer do. The aldehydes, okay. Now, there's a bit of debate about this, but we're going to go with the NSC, all right? The NSC calls this the aldehyde functional group, where you've got the COOH, and this they call the ketone functional group. However, inside this, is the carbonyl functional group. Okay, so C double bond O, C double bond O, this is known as the carbonyl functional group. Okay. This is more important than what you maybe actually realize. I know how important this is because we ask you functional group names and homologous series names, and very often students switch them around. Okay, so now, all right, I will post this on the classroom, but this is really very important. So let's look at the alcohols. The alcohols are a group of organic compounds that contain the hydroxyl group, OH, which has been substituted for the hydrogen in hydrocarbons. Now, there is something I need to bring to your attention. Yes?
For definitions, can we just say that alcohols are organic compounds that contain OH?
Yes and no. What I haven't shown you is the formal NSC definitions, which I'm going to do right at the end of this, which come out of the grade 12 exam study guidelines, and they're all compacted together. You can use this where we are now in grade 10, but as you converge on grade 12, we become more particular about which definitions you use. Okay, this is fine. That's fine what you say there. Okay, so let's talk about the alcohols, and let's talk about this hydroxyl group. So if I take carbon and I have a methane structure and I add hydrogens, and now I add an oxygen that has 6 valence electrons, 1, 2, 3, 4, 5, 6, then what I find is that I land up with an OH structure. Okay, so if I take methane and the OH, you will see that there is actual fact, it's angled because of the lone pairs sitting on the hydrogen here. All right? So this OH, and I need you all to please take note of this, is not the hydroxide ion. The hydroxyl group is all covalent bonding, whereas the hydroxide is an ion. This is not, there's no ionic bonding here. So the hydroxyl group, this OH, does not equal OH minus. This is known as the hydroxyl functional group, whereas this is the hydroxide ion. They are not the same thing. Okay. Would anyone like to venture a guess at what we call this? How many carbons? Sophia, how many carbons? Meth. And how many, and what's the OH? It's OL. So it's methyl. No. Methanol. The suffix that we are going to use is anol. So the prefix is meth because it's one carbon, but the suffix is anol. All right? Methanol. Methanol. Yes.
Why do we add the A and then those?
Because that is, it's like, why in English do I spell pharmacy P-H-A-R-M-A-C-Y, not F-A-R-M-A-C-Y?
Or just because they did.
Because it's of the rule. It's the rule. The same here. We have a thing called the IUPAC naming system. The IUPAC naming system says that's how we call it. It's not methyl. It's not methyl. It's methanol. It's not ethyl. It's ethanol. Okay, let's move on. We've got lots to do.
Mine does say OR. Is that
It should say ANol, methanol, but it's actually anol.
So is that suffix for all of them?
All of them. All right, so if you look here, I'm not going to do all of them. Ethanol, ethanol, 2 carbons, ethanol. There are other naming systems. Ethyl alcohol. Okay, we don't use that naming system, isopropyl alcohol. We use the IUPAC system. Methanol, now, the difference between these two, our bodies can process this to a point. This, our bodies cannot process. This does damage to your body. If you drink methanol, large quantities of methanol, oh my God, goodbye. Bye-bye. All right. Okay. Okay. Propanol. Meth-eth-prop, OH. Why 1 propanol? Where's the OH? On carbon number 1. Right. 2 propanol. Meth-eth-prop, where's the OH? On carbon number 2. But we can also use the following naming system. We can say this is propan 1-ol. Propan 2-ol. Like we've done with enes.
Well, why don't you separate the entire suffix?
Why don't I use?
No,
Really,
pro-
so
So
it's
is that
separate the
all?
entire suffix.
Yeah, that they have, why didn't you separate that?
Because that's not the rule. All right. That's not the rule. It's not pro-2-anol, it's propan 2-ol. And the reason is when we have diols, it's propan 2-diol, propan 2,2 diol, which we're going to get to. There's a whole, the IUPAC, International Union of Physical and Applied Chemists, meet every few years and they keep on adding to the naming system because of the huge amounts. At one stage, they were adding 100,000 organic compounds per year to the library of organic compounds. Yes.
How come we write OH instead of O and then align that with H?
It's the same as in algebra, 2 times x and 2x. Because the OH is viewed as you can write an O line H, it's fine, but we do write the OH because it's a functional group.
Does it make actually a difference on which system you use?
Absolutely, because if you use the other system, you're not going to get the marks in the syllabus.
So, you know,
Oh, you mean between this?
does it make any
but-
difference when you're naming?
It all depends upon how complex the compound is. It doesn't if you use it properly. I would like to suggest that you rather do it this way. If you want to put the 2 in the front, it's fine. I don't mind, as long as you do it correctly. Do not put the 2 between the prop and the and. Okay. All right, so let's take a look at the following. All right. Let us name these. Please do them. I just want to see if there's. Oh, sorry. It starts here, practice 8. All right. If you can please do practice 8, we are near the end of the lesson. So this is the homework. I would like you to name 1. Notice where the OH is. So, Josh, can you see here it's O covalent bond H? You could also just have OH. Sometimes they mix the condensed structural formula and the structural formula. All right. This is an interesting one. I would be interested to see who gets that. Okay. So so do those 2. and then these 4. So there are 6 that I would like you to do for homework.